simulating and downloading counters to Intel FPGA boards with TINACloud, using TINACloud's schematic editor. In our previous videos listed on the screen, we have shown how to create a simple combinational digital circuit, and download it to an FPGA board in TINACloud using schematic symbols, VHDL or Verilog. Now, in this tutorial video, our circuits are counters. The counter is a widely used sequential logic, where the output depends on the sequence of past inputs, and a present value of the input signals. In the case of a counter, the input signal is the clock, and the output's value represents a number. The counter circuit is usually built up with flip-flops. Now let's see our first example, a binary up counter. Start TINACloud, then open the binary counter.tsc file from the TINA examples /FPGA /counter folder. The counter is constructed from 4 rising edge sensitive D flip-flops, counting from 0 to 15. Flip-flops store the count until the next event, when the clock signal produces a low to high transition. The least significant bit is QA. The clock source is 1 Hz for good interactivity. Following the practice, we assign a short clear pulse by PS at the very beginning before the counting sequence to reset the flip-flops. The full name of the circuit is asynchronous binary up counter. Asynchronous because each flip-flop has a distinctive clock, usually from the previous stage. Now press the Transient interactive button. Let's examine the circuit operation. When the clock is changing low to high, the indicator turns red. Then, the least significant flip-flop, U1, will toggle, and this effect propagates through each flip-flop. This ripple phenomenon causes a delay in the nanosecond domain, but if we don't care about an immediate result, short transients are acceptable. Now, before testing our circuit in a real FPGA environment, we need to extend our schematic with FPGA pin connectors as we have shown in our previous video. We will use a TINACloud DE10 Lite Intel FPGA board. We shouldn't forget what resources our FPGA board offers. Regarding the DE10 Lite board, we should note that such a board has clock generators with 50 MHz output frequency. Save the file under the name binary counter PCLK synth DE10Lite.tsc in the My Circuits folder under your account. Now, click CLK1. Then in the Properties window, enter 50 MHz in the frequency field, then click OK. Since the board doesn't provide a 1 Hz clock, we have to apply a prescaler, which will produce that from the DE10 Lite 50 MHz oscillator. Now, let's insert this prescaler as a macro, which has been written in VHDL. Select Insert Global Macro from the Insert menu denoted by a green plus sign. Then, in the Global Macros dialog, select the prescaler and click OK. Place the macro on the workspace, then, pan the circuit by holding down the left mouse button while moving the mouse. Now, you can attach the macro to the input of the circuit, so that the clock frequency will be divided at the input of the counter. The prescaler macro has 1 input, named CLK, and 1 output, named PCLK. The clock frequency at CLK input is 100 MHz, and it is 1 Hz at the PCLK output, by default. To adjust the VHDL code to the board 50 MHz frequency, double-click the macro. Then, in the Properties window, click the 3 dots at the end of the HDL code field. Modify the prescaler less than 50 million expression constant to 25 million. Then save the changes by pressing OK. The prescaler itself is also a counter. When the counter reaches 25 million, the PCLK output is toggled, so that the frequency of the clock at this output is 1 Hz. This is an additional logic to reach slow, human-readable operation speed. Now, add the FPGA pin connectors to the circuit as shown next. Select the first FPGA pin from the special toolbar, then connect it to the clock input of the circuit, before the prescaler macro. Next, double-click the pin connector, then, in the Properties window, click the 3 dots at the end of the pin settings field. In the Device section, click the TINACloud DE10 Lite. Then, select Clock under the Group section, and Max 10 CLK 150 under the Pin section. Click OK to accept the settings. Rename the label of pin 1 as CLK as well and click OK. Now, insert the FPGA pin connectors for the 4 outputs of the circuit and assign them to the LEDs. LEDR0, LEDR1, LEDR2, and LEDR3. Set the LED names to LEDR0, LEDR1, LEDR2, and LEDR3 respectively. Finally, remove the pulse source and connect the clear input of the flip-flops to logic high. The flip-flops will be initialized by the FPGA automatically. Now, let's generate the source files for Intel Quartus Lite. Click the T&M menu and select Export to FPGA Software, then click Intel Quartus. Next, open and extract the binary counter PCLK synth DE10 Lite FPGA export.zip file. Create a folder. We will name our folder Designs, then copy the files, including the VHD and QSF files, into this newly created folder. To produce downloadable content, we first have to create the Quartus Prime Lite project. Start Quartus. Select File, then click New Project Wizard. Enter the working directory name, in our case, C:\designs, and the project name, Binary Counter PCLK Synth DE10 Lite. Click Next. Click Next again. Now, add the source file. From the Designs folder, select the VHD files as source files. Then, click Open. Click Next. In the Family Device and Board Settings dialog, under Device Family, select Max 10. Now, you can manually select the 10M50DAF484C7G FPGA from the available devices. Click Next. Leave the EDA tool settings on default. Click Next again. Finally, press the Finish button. Now, Quartus is initializing our project. We can check the top-level entity VHD file in the Project Navigator. Copy the entity name and set it as the top-level entity under the Assignments menu point. Click Assignments and select Settings. Paste the entity name into the top-level entity field in the dialog. Click OK. Let's add the QSF file as well. Click Assignments and select Import Assignments. From the Designs folder, select the binary counter PCLK synth DE10_Lite.qsf file. Then, click Open. The content of the QSF file will tell the software which FPGA pins are to be used for the logic inputs and outputs. Click OK. Now, to produce configuration data for the FPGA, right-click on Compile Design, then click Start. Now, connect the DE10 Lite with the Quartus machine via USB. As soon as the Quartus Prime full compilation was successful message appears, right-click the program device. Then click Open. Click the Start button to program the device. You will see the progress bar at 100% successful message. And the counter lights come up counting up in binary. If the output code reaches the maximum value of 15, the counter next state will be 0. The simulation of this circuit must be handled with care, because the prescaler has to count to a very large number. Before the output toggles, we have to slow down this module therefore in the simulation. Before modifying the circuit, let's save it under the name Binary Counter PCLK Sim DE10Lite.tsc. Now, change the input clock frequency to 100 Hz. And change the macro code so that the counter counts up to 50, instead of 25 million. This way, we will have a 1 Hz clock coming out of the prescaler for the simulator. To start the simulation, press the TR button. A counter can count not only a series of pulses but other events too. For example, the number of times a push button has been pressed. To demonstrate this, let's go back to our original circuit. Open the binary counter.tsc and save it under the name binary counter btn.tsc. Now replace the clock source with a push button. Delete the clock source, then select a push button from the switches toolbar. Let the push button PB generate a high level when it is pressed and a low level when it is at rest. The low level needs a resistor. Place one from the basic toolbar. Thus, it will work the same way as the button does on the DE10 light board. Start transient interactive analysis by pressing the TR button. Then click the push button, PB, to step the counter. When the button is pressed, a rising edge occurs on the clock input of the first flip-flop, and the counter outputs will produce the next binary code. Stop the interactive analysis. Before implementing this circuit on an FPGA, here we note that the mechanical switches and push buttons have contact bouncing problems. If we press a button once, in the real world, that may generate a series of pulses. To debounce the buttons, either FPGA logic or external circuit is necessary. The TINACloud FPGA board will eliminate the unwanted glitches by a Schmidt trigger circuit, constructing a single low pulse when the button is pressed. The details are on the page 25 of the DE10 Lite user manual. The push buttons' names in the design are key 0 and key 1. Before modifying the circuit for using these buttons, let's save it under the name binary counter btn synth de10 lite.tsc. First, remove the push button and the resistor. These are not necessary because they are on the board and don't belong to the synthesizable logic. Remove the pulse source as well. Now, select two FPGA pins, then place them as shown next. Place the first pin connector and set its parameter as follows. Select key under the group section, then key 0 under the pin section and click OK. Rename its label as clear, then click OK. Place the next pin connector, key 1, and rename its label as CLK. Place 4 more pin connectors and connect them to the logic indicators, QA, QB, QC, QD. Set their parameters and rename them as we did previously. Since we will not need the logic indicators, we can delete them. Now, the circuit is ready for the export of Intel Quartus. Let's generate the source files. Now, connect the DE10 Lite with the Quartus machine via USB. Here, every time the key 1 is pressed and released, a rising edge is applied to the counter clock input, and as a result, it counts up by 1. If we press key 0, then the counter outputs go to 0. Note that each work file is accessible in TINACloud, in the TINA examples /FPGA /counter folder.
For more information, visit our website, www.tinacloud.com. Visit our YouTube channel, www.youtube.com/user/TINA Design Suite.